Dear students, in the last video lecture, we discussed about the formation or hybridization of this molecule. Okay. Now, we will take a similar molecule, just we will change the ligand. And we will discuss about the hybridization or formation of this complex. So you can check oxidation number is +3. Here also it has same oxidation state. So it has electronic configuration of 4s, 3d6. Four S 0, 4p 0, and 4d 0. Now what happens in this complex? We need 6 hybrid orbitals. So in hybridization state, we need 6 hybrid orbitals. But this time what will happen? Instead of taking the inner d orbital, we will take outer d orbital. Okay? And 4d or 3 4d orbitals remain vacant. And the 3d electrons will remain as it is. Now you see 6 pairs of electron will come from fluorine negative ion. Okay? So that's why we have written it as sp3d2, and last time we got d2sp3. Okay, because this time we are using outer d orbital for the purpose of hybridization. This type of complexes are called outer orbital or high spin. Okay, outer orbital or high spin or spin free complexes. Okay, last was a spin. Okay, last time I wrote a spin free, so last time it was not spin free, it was a spin pair complex. Okay, last time for CONH3 whole 6, let me just correct it. CONH3 whole 6 was paired, na? It was totally paired. So this was actually spin paired complex. Spin paired complex. Okay, because there was no free electron or no unpaired electron. Okay, so spin paired complex, but this one is spin free complex as it has free electron or unpaired electron. Okay, so obviously this complex will show paramagnetic properties. Okay, this complex will show paramagnetic properties, and that's why it's termed as high spin outer orbital, because outer d orbital has been used for the formation of hybrid orbitals. Okay, so this is also example of an octahedral complex. Now we will take two examples from a complex which has a coordination number of 4. In these two complexes, the last two complex that we have seen, the coordination number was 6. Okay, the coordination number was 6. Now the complex that we will study will have a coordination number of 4. Okay, so let's take example. So first one is NiCl4 2 negative. You can calculate, the oxidation number is +2 and the coordination number is 4. Now what we will do, we will write electronic configuration of nickel 2 positive. So the nickel 2 positive will look like so 3d8 4s0 4p0. So this is nickel 2 positive. Okay, now in hybridization we need 4 hybrid orbitals. So let's take 1s and 3p. So sp3. Okay, so d orbital will remain same. We have a sp3 hybridization over here. 4 pairs of electron from chlorine. And this is NiCl4. Okay, this is NiCl4. Okay, now see, you just ask yourself and you'll get to know that obviously this complex is obviously paramagnetic in nature because it has two lone pairs, two unpaired electrons, and at the same time, since the hybridization is sp3, the structure will be tetrahedral. It will have a tetrahedral structure and it will be paramagnetic in nature since we have two unpaired electrons. Now let's see one more example of the similar kind. Same thing, oxidation number is +2, coordination number is 4. So nickel positive has 3d8. (4s0), 4p0. Configuration. This is the configuration. Now let's go to the hybridization part. So when we do the hybridization, in NiCN4 we observe that since the coordination number is 4, so we need 4 hybrid orbitals. That's true, we need 4 hybrid orbitals, but this time one d orbital will come, so we get sp2. That means we have taken one d orbital over here, so one 4p orbital will remain unhybridized, and out of 5 4d orbitals will remain unhybridized and 8 electrons are redistributed in it. 3d8 will remain 3d8, but instead of 5d orbitals there are 4 because one has been used in hybridization. Now each cyanide will come with a pair of electron. So this is formation of NiCN4. Okay, NiCN4 with a hybridization of dsp2. Okay, so obviously we can conclude two things. One, it's diamagnetic, and other, it is square planar. It has a square planar structure. Square planar structure because the hybridization is dsp2 and not sp3. In NiCl4 we got the hybridization to be sp3, and that's why it was a tetrahedral structure. ठीक है ना, हमें वहाँ पे sp3 हाइब्रिडेशन मिला तो टेट्राहेड्रल स्ट्रक्चर हो गया. यहाँ dsp2 हाइब्रिडेशन मिलने की वजह से हमें स्क्वायर प्लेनर स्ट्रक्चर मिलेगा, और सिर्फ स्क्वायर प्लेनर स्ट्रक्चर नहीं होगा बल्कि ये diamagnetic in nature भी होगा. Okay, it is diamagnetic in nature. Okay, so this is all about, you know, we have tried 4 examples from valence bond theory. Now let's check some of the drawbacks of valence bond theory. Okay, valence bond theory. Okay, about the magnetic behavior, here we have a section 9.5.2 magnetic properties of coordination compound. So basically magnetic property of coordination compound is just similar to, you know, the magnetic behavior that we have discussed in D and F block elements. In D block element I have told you, you know, I gave you a formula. Okay, the formula was like this: the magnetic moment is equal to root under n into n plus 2 Bohr's magneton. Okay, this was the formula, and what I told you that n is the number of unpaired electron. Okay, so in any complex, you know, in any complex, by knowing the oxidation state of a metal atom, the central metal atom, you know, you can predict whether it is paramagnetic or diamagnetic. Okay, and see why we are discussing the magnetic property, because see what is happening in the, you know, we got these two complexes. One was like this and one was like, you know, this, and we have seen that in both the cases cobalt is in +3 oxidation state, and this was diamagnetic and it was paramagnetic. Okay, it was paramagnetic, though the oxidation state of the cobalt was same. Okay, okay. Now see, so on the basis of hybridization we have explained this dia and paramagnetic behavior, but though we have discussed the para and diamagnetic behavior, but we observe that valence bond theory is not absolute. Okay, it has some flaws. And what are the limitations of the valence bond theory? So basically it is based on some assumptions. Okay, some assumptions like you see the formation of D2sp3 and sp3d2. Okay, so we must know whether it is high or low spin in order to, you know, understand whether it will be D2sp3 or sp3d2. Okay. Second, it does not give quantitative interpretation of the magnetic data. Okay, that means we can, you know, find out whether a complex is paramagnetic or diamagnetic in nature, but it will not tell you how strongly paramagnetic one complex is. Okay, so no quantitative idea. It does not explain the color exhibited by the coordination compounds. Okay, so it will not tell us about the color, how coordination compounds are colorful. Okay, it does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of the coordination compounds. Okay, it does not make exact prediction regarding the tetrahedral and squalpyramidal structure of the 4 coordination compounds. We have seen in example that it's very difficult to understand that why in case of cyanide we got DsP2 and why in case of chloride we got sp3 hybridization. Okay, there was no explanation, it was based on assumptions basically. Okay, it does not distinguish between weak and strong ligands. अब ये वाला जो पार्ट है, ये वाला पार्ट ऐसा है कि कोई लिगेंड स्ट्रांग हो सकता है, कोई स्ट्रांग हो सकता है, कोई वीक हो सकता है, या स्ट्रांग वीक हो सकता है, ये हमें पता नहीं चल रहा। हमें पता नहीं चल रहा कि लिगेंड्स के वजह से कॉम्प्लेक्स में कोई चेंजेस आता है या नहीं, कोई लिगेंड वीक या स्ट्रांग हो सकता है या नहीं। ओके, सो इन सब चीज़ों को, इन सब प्रॉब्लम्स को हम काउंटर करने की कोशिश करेंगे। जो हमारा नेक्स्ट थ्योरी होगा वो होगा क्रिस्टल फील्ड थ्योरी, CFT। तो जो नेक्स्ट वीडियो है, नेक्स्ट वीडियो में हम क्रिस्टल फील्ड थ्योरी के बारे में पढ़ेंगे, उसके बारे में डिस्कस करेंगे। ओके, थैंक यू।